Hello students, this set of notes is continuing on with our Taylor and Maclaurin series, and this time we're looking at the Lagrange form of the error term. So remember, Taylor and Maclaurin give us ways to approximate a function with a series. So if I approximate it with a partial series, then it's not going to be exactly equivalent to my function. So it'll only be it'll only be exactly equivalent if I continue to infinity. And if I stop part way, then I'm going to have some sort of error. So this error is given with this formula. So we're saying that the error is going to be the value of the derivative calculated for some value c that's between 0 and our x value, where we're looking to approximate the function. So we're approximating the function at some x. My error term takes this form. So value of the next derivative evaluated at c, x to the n plus 1 over n plus 1 factorial. If I go for a Taylor polynomial, then my Lagrange error term includes the x minus a. And then my c value is between a and x. So this is the same for Maclaurin, except for Maclaurin we have the a value is 0. So that's why it looks like this. All right. So if my limit as n goes to infinity of the error term is 0, then the Maclaurin series for f of x is the same as the function for f of x. So I'm going to use this when I get down to example 2. But let's start with example 1. So example 1 says, find an expression for the error term approximating f of x equals e to the x by the second degree Maclaurin polynomial. So I know with Maclaurin, then that tells me that my a value is 0. If I've got the second degree Maclaurin polynomial, I'm looking for the r sub 2 term of x. So I'm going to apply this formula. So that's going to be the third derivative evaluated at c, x to the third over 3 factorial. Well, my f of x is e to the x, so the third derivative of x is still going to be e to the x. So now my c value is going to be between 0 and I want to approximate 0.75. So my c value is going to be between 0 and 0.75. So filling this in, my r2, and now I want to find it at 0.75, is going to be e to the c times 0.75 cubed. 3 factorial is 6. Again, my c has this range, so this implies that my r sub 2 of 0.75 is going to be between when I evaluate at 0 and when I evaluate at 0.75. So I'm going to want to put those in my calculator, see which one is bigger. So I'll have, obviously when c is 0, then I'm just going to get 0.75 cubed over 6. Oops. Let's try that again. Cubed quantity over 6. Or I could multiply that by e raised to the 0.75. So here's my error bounds. I'm going to be between 0.0703 and 0.1489. So it said, give an upper bound to 4 decimal places. This one is going to be my upper bound because it's the greater of the two. Let me just, yeah. All right, so that's my second the second Lagrange error term for the second degree Maclaurin polynomial for e to the x. I'm going to keep talking for a second. So what this really means is if I take my T2 Taylor polynomial, we know for e to the x that our Taylor polynomial, hopefully you remember, is going to be 1 plus x over 2. And this is, x squared over 2. So this is my T2. So if I approximated e to the 0.75 using this polynomial, this is how much I would be off by, a maximum of this much. So let's look at that. So if I did 1 plus 0.75 plus 0.75 squared over 2, and compare this to e to the 0.75, if I take my difference, I get 0.085, which is in fact between those two numbers. So that's what I'm talking about with my error of approximation.